everybody. Today is the 22nd of April 2026. We are going to look today at a model very important for logistics called economic order quantity, okay? And we are going to make three different hypotheses and then we get three different solutions. The parameters we're going to use throughout are the demand measured in parts per time, the cost euros per time or money per time, the setup cost A, okay, which is measured in euros, is the money it takes to change the machine from one product to another product, okay? For instance, if you're producing strawberry yogurt and you want to produce lemon yogurt, you want to stop the machine and clean it so that you don't have a taste mixture. And then the inventory holding cost measured in money divided by time times parts, which is the money it costs to hold inventory, okay? We're going to take three different models, okay? So the economic order quantity, EOQ, model number 1, okay? It takes two hypotheses. This is something we are going to assume, okay? Always in math, hypothesis is something we assume. The first hypothesis is immediate. This is the easiest. Immediate delivery and production. Okay. So the second hypothesis is constant demand. Of course, when you order something in Amazon or in if you order a car or something like that, it is impossible, physically impossible, to immediately produce the product and deliver it in 0 seconds, okay? This is just some ideal that we are using to start modeling the system. But this is an ideal, okay? This needs to be highlighted. Let's paint in a little graphic how this model works, okay? We want here to have the time, and we want to represent the inventory, function, okay, as a function of time. Okay, and we start with our delivery with our inventory in 0, in time equals 0, and because we have immediate delivery of some quantity, we can say that in time 0 we have some order quantity, some quantity ordered, okay, that we are going to call Q, and this is our order quantity, Q. So the first hypothesis is that we have immediate production and delivery, okay? So this line is vertical, because we have in this model immediate production and delivery, okay? So we continue, and because we have constant demand, the inventory is going to deplete in the form of a line because the demand is constant, so we take every time interval we take the same amount of inventory out of the stock. So here the second remark, here this has a constant slope because demand is constant. Okay. And the time it takes to deplete the Q inventory is Q divided by D. Okay, this is this time. Q divided by D. Okay. So this is our model, and this repeats many times. This repeats many times. As I said, this is an idealization. Okay. But always running the same. So this we called the frequency of delivery. How often we are going to deliver. So, any questions to this? No. So we are going to represent our cost function. Which is going to be called epsilon of Q. And the cost function is going to have different parts, okay? So in this model, we have some cost because we have some inventory. We have some setup cost to put the machine ready to production. And we have some production cost to produce a cost, maybe some material cost and stuff like that, okay? Good. So how does this works mathematically? Let's paint again some graphic. This is the time. This is the cost function as a function of Q. Okay. So the cost of inventory is some holding inventory cost, H. We saw it in the parameters here. Okay, how much it costs to have one part in our inventory multiplied by the average inventory. So of course the average inventory here is simple. The average inventory is Q divided by 2. Okay, so this is the inventory holding cost. Per unit, and this is the average inventory. If we multiply these two, we get the money it costs to hold the inventory. Okay, so now the setup cost. So every time we do a setup, we pay A because of the parameters we have there, setup cost, multiplied by how often we change the machine over, how often we set the frequency. So we get that. This is the setup cost. And this is the frequency of setup. And the production cost is some cost we have because of production times the demand, how many parts we produced. Okay, so this is the cost to produce, and this is the demand. Good. Okay, any questions on this? Let's represent these curves. Okay. Sorry, this is wrong. This is not time. This must be Q. Okay, we are looking for the economic order quantity, so this needs to be Q. So depending on Q, the first inventory holding cost times average cost. This is a line in Q. Okay, it's linear. So what we get is a simple line here with some slope. It's positive. Okay. So the first thing we notice here is that our inventory holding cost is going to increase. The cost of inventory is going to increase linearly with the inventory. This is very logical because the more inventory we have, the more storage capacity we need. Okay? So the cost of inventory increases linearly with the inventory. Okay? Good. So the second, the setup cost, is going to be some line like 1 divided by Q. It's going to have this form. Setup cost. It's going to have this form. Meaning that the higher the order quantity, Q, the less we change over the machine. Okay? The higher the order quantity Q, the less we set up the machine. So we have less setup cost. And the last is just a constant. It doesn't depend on Q. So this is very simple. The production cost is in this model constant and looks like this. Okay? Any questions? Well, what we do now is we simply add up all these three curves and we get to this result. Okay. We are looking for the most economic order quantity, so the minimum of this function is going to be achieved at Q star, and the cost related to this Q star is epsilon of Q star. I say epsilon, I like to say epsilon is, could say y or something, but I like to say epsilon. So we look for Benjamin's my superhero here. It reminds you that we look for the economic order quantity Q star that minimizes the cost y. Okay? So, because we look for the minimum of a function, what do we do? Can somebody tell me? Hello? How do we find the minimum of a function? Hello? You should know this. How do we find the minimum of a function? No? Okay, this you should know. So we have our function epsilon of q, h q divided by 2 times a times d divided by q times plus cd. The minimum of this function is the first derivative of epsilon with q equals q star. equal to 0. So the first derivative of this function in q equal q star should be 0. So the first derivative of this function is h divided by 2 plus minus ad divided by q square in q equal q star equals 0. This will be h divided by 2 minus ad divided by q star square equals 0. Okay, we can say q star of the model 1. So q star of the model 1 is going to be square root of 2 times ad divided by h. Okay. If we plug in this value in the cost function, then we say this is h times q1 star divided by 2 plus ad divided by q1 star plus cd. Okay. And we make some simplification, meaning that because CD is constant, CD is approximately 0. Okay. This is an approximation. To make things a little bit easier, then we have that epsilon of q1 star equals h times square root of 2ad divided by h divided by 2 plus ad divided by square root of 2ad divided by h, and this yields that the cost associated to the economic order quantity, the minimum cost in this model, is square root of 2adh. Okay. And this is the solution of the problem. Okay. Any questions? Any questions, please? No. Good. Then we continue with the economic order quantity number 2, which is called the supplier model. Okay. The first in the first one we have the hypothesis of immediate delivery and production. So this is the ideal model and constant demand. Now with the supplier model, we have different hypotheses. So the model is going to be a little bit different. In the first model, we didn't accept stock out. Here, right after hitting 0, the thing just jumped back up. In the second model, we accept stock out. meaning we can go in the negative, orders that we still have not delivered, in which supply has a backlog of orders, but still supply and delivery and production are immediate and demand is still constant. So what we are adding is basically that we can go in the stockout in this model. Okay, so the new parameters we need are P. This is the cost associated to not immediate delivery, cost per not supplied orders. Some customers might not wait for us to deliver and they might go to the competition. Okay, so if we cannot deliver, they go. And then S is the inventory after delivery, measured in units or in parts. And we say that the backlog as a result is Q minus S. Let's represent this in form of a graphic, okay, to better understand it. Let's say this is the time. This is our inventory. Okay. We say there is some inventory after delivery. So let's say this is S. Better here, S. This is the inventory after the delivery. We start our travel with some backlog in T0 because of the first hypothesis, of the second hypothesis, delivery and production is immediate. So we deliver immediately. And we deliver Q, okay, so this quantity that we deliver this is Q. So Q minus S is the backlog. This is Q minus S. This is the backlog. Okay. And because we have a constant demand, we go down and deplete this inventory in a constant speed. That's why this is again like a saw, okay? Going down, then we go up again, and so on and so forth. So in this model, we have here some important times. This is T1, is the point where this touches 0. From there we are depleted. So this is T1 and this is T2, the moment in which we deliver. Okay? So simple geometry, T1 equals S divided by D. This is this triangle, S divided by the slope, okay? And T2 is Q divided by D. This is just because of the geometry. So the cost function is going to be a function depending on two quantities, on two variables, Q and S. How much inventory after delivery we allow. This is something that we can decide or is based on the process. So we have some inventory holding cost. We have some backlog cost. We have some setup cost. We have some production cost. Okay? So the inventory holding cost equals the holding cost per unit, the average inventory we have, because now the average inventory is not Q divided by S, but S divided by Q divided by 2 is S divided by 2. Okay. Average inventory is here S divided by Q by 2. Sorry, it's a 2, not a D. Times the time to consume the inventory times the frequency, how often you do this. So this is, as I said, this is the holding cost per unit. This is the average inventory. And this is the time to consume inventory. And this is the frequency, just as in the previous model. How often? Okay. So the backlog cost equals P, this is the backlog cost per unit, times Q minus S divided by 2. This is the average backlog. Okay, average backlog, same logic as before, is the average of this, okay, is Q minus S divided by 2. This is the average backlog. S divided by 2 is the average inventory. Okay, times the average backlog times the frequency again, same thing. I repeat, P is the backlog cost per unit, the average backlog, times the frequency. Times the frequency, how often. Okay. Okay, I think my thing went away. I need to log in again. Something happened there. So I need to make presenter. So let's do it. The first derivative of epsilon to q equals in q star and s star equals minus hs star square divided by q star square plus P multiplying q star minus s star divided by q star no wait no yeah you're right P q star minus s star no I'm gonna do it a little bit more slowly because otherwise I guess you will get lost. So this is D cancels with D, okay? Let me simplify the function a little bit so that we can operate better. So the first derivative of epsilon to q in q star and s star equals minus h s square star divided by q star square. Okay, this is simple. Plus this is this equals this part equals P divided by PD divided by 2 times 1 minus S divided by Q. Okay. So if we do that, we get PD divided by 2 times S divided by Q star square minus AD divided by Q star square, and then the other one is 0. Okay. So, and the second derivative, this needs to be equal to 0. The second derivative of epsilon to Q star and S star equals 2 times H S star divided by 2 times Q. 2 goes with 2. Plus or minus, better said, PD divided by 2 times Q star plus 0 plus 0. Okay. So if we solve these two equations, what we get is that the S star of 2 equals square of 2AD divided by H times square root of P plus H. So the backlog allowed is S is the inventory after delivery. I mean is P divided by P plus H, which is smaller or equal to the first economic order quantity. The second economic order quantity equals square root of 2AD divided by H times P plus H divided by P equals Q1 star P plus H, and this is bigger or equal than the economic order quantity of 1. Okay. This is the solution to our second model. Okay. Any questions?
I think there's a mistake in the second equation.
Where?
In the square root in this Q star 2. And the square root at the end.
You're right. Sorry. I was just too fast. Thank you. Yeah, you're right. Thank you very much. Okay, so the last model, of course, this can be made in many models. Okay, so we just are going to look at 3 of them. This is called the manufacturing model. Without backlog. Okay, so the hypothesis here is we have constant demand, no backlog, but now production and delivery are not immediate. Okay, so we have a parameter now, a new parameter. Called K, which is the production rate. It's the speed of production, okay? So our graphic looks now a little bit different. Important is you understand why this looks different, okay? So not only do the math, but understand what is going on in the concept. So this is the inventory. We start again with 0. We get an order, but because now we cannot produce immediately and deliver immediately, it takes some time to achieve to deliver the quantity, okay? This is Q. So it takes some time to deliver the quantity, and it also, because demand is constant again, the depletion of the inventory is also a line, okay, so a different slope, and then it starts again from the beginning, okay. So here again we have a function y of q equals holding cost of inventory plus a setup cost plus a production cost. Okay. So in a simplified way to put it, the holding cost of inventory, now we have the average inventory. It's not going to be what we had before, but a little bit different. Okay, because we have two triangles. So the average inventory is Q divided by 2 times 1 minus D divided by K. K is going to define this production speed, okay? So the holding cost of inventory is H again times Q divided by 2, 1 minus D divided by K, plus the setup cost, same as the same, AD divided by Q, plus CD. The first derivative, as I said, we don't have a backlog, so this is just only one variable. To find the minimum of this function, it's just getting to the first derivative and making it 0. So this is going to be q star 3. This is going to be q star 3 divided by 2, 1 minus d divided by k, minus ad divided by q star square 3 equals 0. So our q star 3 will be equaling square root of 2ad to ad divided by h 1 minus d divided by k. Okay. Here it's important to notice that if the production rate is infinite, so k is much bigger than d, this means we are super fast in the production. We are super fast producing compared to demand. Then 1 minus d divided by k is almost 1, and then q, the economic order quantity of the third model, is almost the same as the economic order quantity of the first model. Okay? In the same manner, if we do the same calculation as we did in the first model, the best cost for Q3 star equals square root of 2ADH 1 minus d divided by k. You can do it by substituting Q sub 3 star in the formula, in the cost function. So here, the same, again, if k much bigger than d, then the cost, basically the models become the same, and we can approximate the third with the first model. Conclusion. The more flexible the production, the bigger k, the better we can adapt to demand changes. Basically, K is saying how big is this slope, okay? So a very low K would be like this. So this is K is smaller than D, and this way is K is much bigger than D. Okay. This is the geometric meaning. Let me paint it, I guess. Maybe it helps. So this is time, this is inventory. And if K is much smaller than D, we have this situation. If K is much bigger than D, we have this situation. Okay. So, any questions? Good. So now you know the economic order quantity. If you want to learn more, again, go to the book Factory Physics. I strongly recommend that you read it and buy it and study it if you want to dedicate professionally to this business. All right.